Good afternoon if you're watching this in the afternoon. If you're not watching it in the afternoon, what are you doing up so early? Either way, we are talking today about new functions from old functions. So this is going to be a lot of your transformations of the parent functions that we just talked about. And the second half of this video, day 2 of the lecture, if you want to think of it that way, we'll be dealing with operations on functions and composition of functions as well as their domains, which will go a little bit deeper than what we did last year. So first, let's talk about transformation of functions. Well, okay, so first up, we're going to have vertical and horizontal shifts. Vertical and horizontal shifts are going to be when you take C and then you add or subtract it, either inside or outside the function. If you remember my rule on this, remember everything that's on the outside is going to follow exactly how you think it should go, while everything on the inside is going to be backwards. Okay, so outside also means that we're going to be moving stuff vertically. Okay, so if I add C to something, add C to a function, then what I'm going to do is I'm going to take just the regular parent function I had, and I'm going to move that parent function C units, let's just leave it easy, up. Well, naturally, if I was to subtract C, it would move it C units down. We like those because those make sense. They're outside the function. You can think of it, I'm taking the Y coordinate and then I'm adding this many units to it. That makes sense to me, at least. If it's on the inside, it's going to be backwards. So this minus C, since it's on the inside of the function, we're looking at it moving horizontally. And so minus C, I would think move it to the negative side, to the left. So I got to think opposite. And so instead of moving it to the left, if I'm subtracting C on the inside, I'm actually going to move it to the right. Whereas if I was to add C, I would move it left. So let's just suppose that my parent function looks like this little wiggle right here. Okay? That little wiggle, if I was to take it and add C units to it, I would just take all of them and they would all come up C. Whereas if they was to come down, notice that the whole thing moved. Let's say that would be f of x minus C. It moved it down. If it's inside the function, and I just move it directly, I'm trying to keep the same shape. Kind of did rough on that one. But if I move it to the right that many units, it's going to be f of x. Let's say it moved to the right, so it would be opposite, minus C. Whereas when it moves to the left, that's whenever we're doing f of x plus C. Okay, those were the basic ones. Those are called translations because it's a rigid transformation because we're not changing the size or the shape of my original function. All of these are going to be non-rigid whenever I have a vertical or horizontal stretching or reflecting because it's going to either change the shape of it or the size. So first up we have when I'm multiplying C times f of x. If it's being multiplied by a constant, we are going to, everything on the outside makes sense. So we're making it bigger. We are stretching the graph of f of x. And we're going to go vertically. I'm just going to put vert there because I don't have much room by a factor of C. And in what it's being stretched from, remember, it's being stretched away from the axis. I'll show you that on the next slide. Now, if it's being multiplied by a fraction, 1 over C, or you can think of it dividing by C, then that's going to go the other way. That's going to compress. So you can think of it if it was like 1 over 2, 1/2. I'm going to push it down towards the axis. And it's still going vertically because it's outside. Remember, everything that's on the inside is going to be horizontally. So I know these next two are going to be horizontally, but let's make sense because it's going to be backwards. So I'm multiplying right there. So I'm thinking about multiplying it. It should make it bigger. It does the opposite, so it actually compresses. And if I use a fraction here in front, a fraction between 0 and 1, it's going to actually stretch it. And then we have some reflections. Reflections follow suit. All right, that negative sign is outside. Okay, so everything outside the function messes with it vertically. I'm going to reflect this graph vertically. So that'd be about the x-axis, and it reflects it. Whereas if the negative sign's on the inside, it's still going to reflect, but we are going to be going horizontally on that. So whatever's on the left side of the y-axis is looking in a mirror and it appears on the right side. Whatever's on the right appears on the left. I'll take a little bit of practice. Let's look at some of these. I don't know if I'm going to fill up and do all of them, but let's take a look at some. Let's go back to my little swoop thing right here. F of x right here in the first quadrant. Okay. So first up, let's just do a c times f of x. C times f of x, what it's going to do is it's going to stretch this red line away from the axis. So ideally, like if I'm stretching it by a factor of 2, since I'm 1, 2, 3 units up, I would start 4, 5, 6 units up. And it's just being stretched away from the axis. I'm not pulling out a ruler on it. I just need to tell that it's being stretched. And so this would be an example of c times f of x. 1 over c of x would just be if I'm just taking my foot and I'm just stomping down real hard on this red line. This would be 1 over c times f of x, where c is a number greater than 1. Let's talk about the reflection. That one's being reflected horizontally. It's being reflected in the y-axis. I just think about it horizontally, where I'm pulling a negative through on the inside. Because if I come down, ooh, it's really hard to do upside down. Close enough. I think you know where I'm going with that. That's going to be negative f of x. Comes down. I might as well do them all. I'm going to scrunch this in towards the axis. So this green right here would be my f of x. I'm scrunching it in, so it would be f of c times x. Whereas if I was pulling it away from the axis, it would be f 1 over c times x. So as you can see, some of them do look similar. It's hard for me to tell if you're just trying to move it to the left, like we did earlier, or if you're trying to compress it towards the y-axis there. So make sure you're doing the best you can with it. This is a non-rigid transformation, so it's been kind of pushed together a little more. It's standing up a little bit more straight. Okay. Okay, so what we're going to do is we're going to take one of our parent functions. We're going to take y equals f of x, and we're going to graph the following transformations. It says given the graph of this. I would hope you know what this is. If you haven't, pause the video, go do some homework. Okay. If you have done it, then you should know that this guy is going to be the swoop. Okay. So this minus 2 is on the outside. Outside the function, I'm thinking translation. I'm thinking vertically. It's being subtracted. So yeah, pretty much all my y values just lost 2. So I'm pretty much just checking these 2 primary points right here. I'm making sure you move 0, 0 down 2 units, and that you move 1, 1 down 2 units. If you get those 2, the rest of the swoop should follow pretty easily. What's this square root of x minus 2 going to do? Some people sadly argue it's going to do the same thing, but look at the minus 2. It's inside the function because it's inside the square root. Everything's opposite. So I got to think. You can think of it this way. Let's not think of it that way. I don't want to go there yet. So this minus 2, I would think come over to the left 2, but it's going to be opposite. I'm going to come over to the right 2. Draw my initial 2 dots, and that blue swoop moved to the right 2. y equals negative square root of x. That is a vertical reflection. Some pretty basic ones compared to some of the ones that we did last year. I'm going to leave these last two up to you. Go ahead and hit pause on the video, and I'm going to erase these 3 lines that we did, and I want you to draw the last 2, and then hit play once you're done and see if your swoops end up where mine do. And here we go. One quick thing, notice that my green line right here on this 2 square roots of x still is right here, because if I double this distance away from the x-axis, I'm still landing right there. It's being pinned down right here, and then this blue line is just being stretched up to where the green one ends up. I love working this one with students. It's good. It's a good problem. It frustrates them a little bit because they can't really tell what's inside the function. They know it's going to be a quadratic. They know it's going to be a parabola, but they look and they're thinking, well, the 6 and the 10 are on the outside, but the 6 is with the x. Well, what happens on this one was we need to create our own inside and outside. We saw many ways to graph this last year. We had a x equals negative b over 2a trick that we could plug in to get the vertex, and then we knew that 10 in this problem was going to be my y-intercept. We can hang on to that a little bit of knowledge if we want to, but I'm wanting to graph this using transformations. So I'm needing a single x on here, and I need a definite inside the function, and I need a definite outside the function. Let me give you a hint as to what we're going to do first. Actually, I'm going to come down here. You're going to love this. Just wait. See what I did there? I would argue so far I have not changed the value of that function on the right side. I just put in some parentheses, and I left a very convenient space. And yeah, you know it's going to go there. I'm going to take half of this 6 right here and square it. I'm going to complete the square on it. And it gave me 9. And whatever I do on one side of the equation, I've got to do on the other. Okay, so let's clean this up a little bit. So I'm going to actually now subtract 9 from both sides. And the whole point of completing the square was it's going to give me a nice binomial squared. So x plus 3 squared plus 1. Now I just have my parabola, my basic parent function of a parabola. It's used to sitting right here, but now it's been moved to the left 3 and up 1. So I'm going to take my parabola. Now instead of sitting on 0, 0, it's sitting on negative 1, 2, 3, positive 1. Oops. This is a solid line. I want Mr. Lovely to grade this line because that's where it's supposed to be. So some trig in here. Last year when we did this, I said, hey, there's just a period change. Let's just recalculate the period and then we'll scale our axis. Let's take it a step further. Now that we know about transformations, let's link what we did in pre-calc A to pre-calc B and see if we can make sense of these sine, cosine, tangent functions using transformations. So normally sine is the one that goes through the origin. Oops, I'm going to do a dotted line on this. And we know there's a period change, and we had a formula for the period change, 2 pi over b. But let's look at this. This 2, is it inside or is it outside the function? It is inside my function. I am actually taking sine of not just x, but sine of 2x. So I'm going to consider that inside the function. And it's multiplying, right? So this is going to follow just the f of x and then c times x. So that was my compression. So what's going to happen is all of these hills and valleys are being compressed back towards the y-axis. Feels like I skipped one. No, I didn't, but maybe about like right there. So now my graph, the period on it is much smaller. Let's see, about halfway back right there. It's been squished together. It's definitely had a period change where the wavelengths aren't nearly as long. And so it looks kind of rough. I could have done that a little bit better. Probably plotted more points. It would have been fine, but I think you get the idea. me give you a little bit of background on this problem. I grabbed this picture from the book, and what this is this is the length of daylight in different cities in the U.S. according to their degrees, oh boy, longitude. All right, make sure I said the right thing there. Their degrees longitude. So if something is at 20 degrees north, is that longitude? Oh my word, I got it backwards. Latitude. Definitely latitude. Latitude goes up. 20 degrees latitude. I won't even edit that out. I'll let you laugh at me a little bit. Just don't tell your social studies teacher. So, looking at this, I will be able to tell how long the daylight is. All right. So, this one's a lot of fun to work together in class as well. I really enjoy it. It makes you think a little bit. And so, I'm wanting to put this into the model. Let's see, it's a length of day versus time. So the model is going to look something like this. Like the length of day by time is going to be, let's see, we have the amplitude plus, oh, not plus, I'm doing this out of order. Amplitude times sine of B T minus C. I'm thinking, man, this guy's using way too many variables. I'm trying to use the same variables I did last year, where D is a vertical shift, C is a horizontal shift, B is my period change, and A is my amplitude change. Okay? And what I want to do is I want to find the function that models the daylight in Philadelphia. And Philadelphia landed where this blue line is, at 40 degrees north. Now you can start anywhere you want to in this. I'm just going to start at the beginning. I think that amplitude is going to be the easiest thing to find. Remember, my definition of amplitude is going to be half the distance between the max and the min points. Well, on this blue line, this max point fell at 15, and the min point, it looks like it's over here at what? 9? Close enough. I'm just going to use 15 and 9. It's a little bit off from what we'd have, but that's really close to 15 and 9. Might be a little bit north of 9. Maybe do 9.1. I'm just going to use 15 and 9. So half the distance between 15 and 9. And so that comes out to be 3. That makes sense because like right here's the middle. And if you look at it, my amplitude is how far up and how far down I go from the middle. And that's right around 3 units. So I feel good about that. So I've got my A. It's going to be 3. Now, I chose a sinusoidal function. You could have definitely done, you have to do sinusoidal, but whether you do sine or cosine is up to you. I'm choosing sine because I'm kind of imagining that the axis that it would run through, would be right around here. Oh, that's unfortunate. Right around there. Maybe not exactly there, but I'm seeing the hill and the valley a little bit easier than I'm seeing just one valley. So. Or one hill. So maybe you were thinking cosine on this. It can definitely be worked like that, but I'm just not necessarily working it that way. I think next D is the easiest thing to find because D is how far this thing's been shifted. How far the midline's been shifted. I just erased the midline, but we can tell this thing's been shifted up 12 units. So it would make sense for D to be 12. If you need a formula for it, it's still going to be half the distance, or it's going to be the max and min added together, and then half that distance, which does give me 12. So I know that this guy back here is going to be 12. See, I know this is sine. I know this is t. And so all I need to get my hands on are B and C. Okay? B and C. The only formula we had that related B was we said that period, switch colors so we can follow, the period is 2 pi over B. Well, I'm wanting to know what B is. I can't get B from this, but I know what the period is. This throws off a lot of people because they say, well, this blue line does not come back to where it started right here. Where would it start? How long would it take to complete one cycle on this blue line right here and get back to where you started? I would argue right around a year, 365 days. So if I solve this for b, I can simply move the hat, and I get 2 pi over 365. All right. Last up, we have C. Remember, C is going to be my horizontal shift. And I went ahead and put a minus sign in there because I see that I shifted it to the right. Okay. Now, I think I left off a caption on this. But this mark right here is actually going to be March 21st. It's the 21st day of March. I'm guessing that's the first day of spring, maybe. That would make sense. And so if that's the first day of spring, this thing has been shifted over that many days. If you don't include a leap year, it's been moved over 80 days. March 21st is the 80th day of the year. So I think it makes sense if I just put a minus 80 right there. It's been shifted over that far. Leave your answer like this. This is going to be fine for me. Looks like there's a negative in there. There's not, I assure you. But this right here is going to be good. So in Philadelphia, if I'm wondering how long, today when I'm making this video, it is August the 25th. If I'm wondering how long a day is on August 25th, I can either estimate it by about where this would go up to, right here, or I can calculate what day of the year August 25th is, and plug that directly in for t. Suppose it's, I have no idea. Suppose it's the 287th day. I'm just making something up. I could just plug in 287 in for that t right there, and it would tell me the length of time that I'll have daylight on that day. Pretty cool little function. You need to test me on that 287, see how close I am. I'm curious. I'm going to do it after the video. One thing that they snuck in this section is they snuck in some absolute value. We talked about absolute value and defining it as a piecewise function earlier, but what happens if they just have a parent function, x squared obviously, that's been moved down 1 unit, came down 1 unit, but there's absolute value around it. How am I supposed to work a v into that? A v kind of works into it. Instead, what's going to happen, what I'd rather you think of is all these y values right here have to equal something that's non-negative. It has to be positive, or let's say greater than or equal to 0. There's no way to get anything negative on this, meaning that my final answer should be, yeah, these lines that come up right here, but I can't have anything negative down here. So what that does is it just kind of bubbles up and reflects over. It comes up. And so the graph actually does look like that. You might be saying, where's the V at? Well, these are actually sharp corners right here. And so that will, your V kind of got split up on each side. This is a good spot to pause the video, take a break, especially after that 40-degree Philadelphia problem. And then, because we're about halfway through the video right now. And so take a break, come back, and then we will do combination of functions. Combination of functions, or as I refer to them often as operation on functions, is just going to be simply where you're given two functions and you're asked to add, subtract, multiply, or divide them. Okay. Now, the way that they write it is kind of weird. For instance, if they write it like this, f plus g of x, what they're actually wanting you to do is take your f of x and add it to your g of x. So you can imagine what the rest of these are going to look like. F minus g of x, yeah, you're just subtracting. Order will matter on this one. Make sure you're doing f of x and you're subtracting off g of x. F times g of x, I'm going to multiply f of x by g of x. And it works for division too. Just make sure that your g of x is not equal to 0, because that would throw off everything. Okay? And we did all these last year, and we said thank you, Mr. Lovelady, for those problems. But what we didn't worry with was domain. All right? Whenever I do domain on this, so the domain of this first one, f plus g, is going to be A intersect B. Okay, where A and B are going to be the domains of f and g. Let's talk about what intersect is. It means that suppose I have A over here, and I have, no, that wouldn't work. And I have B over here, okay? A intersect B, or this is also known as A and B, it means that the function, whatever's in A and B, this shared region is going to be the domain. We'll look at that with some numbers in just a minute. That's actually going to be the domain all the way down. A and B, and then finally down here, it's going to be A and B, and like I said, as long as g of x is not equal to 0. So let's look at some. The math behind this is pretty easy, but I want to really focus on this domain that we skipped last year. I'll leave that little drawing up there. Have that help us. Okay. So it wants me to find all of these, f plus g, f minus g, f times g, f divided by g. Okay. So f plus g, according to the last slide, all I got to do is take my terms and add them together. And that's really all that's going to be, that's all I have to do on that. I'm done. I can't combine those because they're not like terms. So whenever I subtract them, yeah, I'm just going to throw a minus sign between them. I can't combine them. F times g. That one will go a little bit further. Since I'm multiplying or dividing and they're both inside the house like that, they're both inside a radical, I can distribute that and just get the square root of 4x minus x cubed. That does work on that. If you have a question during an assessment if that works or not, come back and ask me. Say, hey, does this go further? I'm like, yep, sure does. Excuse me. F divided by g. This is not going to be as easily simplified since it has this function of x down here at the bottom, and function of x is more than one term. One thing that does make it look a little bit better is I could write it as one fraction. Since they're both underneath the square root, the fraction can just go underneath one square root. And so this would answer all the questions on find f plus g, f minus g, f times g, and f divided by g. However, I'm going to be asking on the upcoming assessment for the domains as well. So let's think about this. We could definitely find the domain of this whole thing right here. It gets a little bit tricky because there's two square roots right there. But instead, what I want you to think about is the domain of this f of x right here. The domain of the f of x is going to be the swoop. Well, I know if I have a swoop and it's a square root, whatever comes out from underneath the square root has to be positive. So x has to be greater than or equal to 0, giving me a domain if we're doing the interval notation of 0 to infinity. So what I want you to think about is this part A right here is all the numbers from 0 to infinity. Okay? While B, this is going to be a little bit trickier. B, let's see. If I add x squared and take the square root of both sides, I get something that's kind of weird. I don't know if that works with that square root and that inequality in between, because it gave me 2 and negative 2. Why do I need 2 and negative 2 when 2 is bigger than negative 2, but x has to be smaller? Let's make a number line and see what works. Okay. So if I plug in, let's just plug in 0. 0 is an easy number to plug in. If I plug in 0, good stuff happens. 4 minus 0, we like that. Let's plug in 3. 4 minus 3 squared right there. That's going to be 4 minus 9. I get the square root of something negative. I don't like that. All right? I don't like square roots of something negative. So the only thing that's going to work on that is everything that's between negative 2 and positive 2. So this B bubble over here is negative 2 to positive 2. And so what my domain is going to be on my first three, on my addition, subtraction, and multiplication, is going to be what overlap I have here. What number is included in A and also in B? Well, A is all the numbers from 0 to infinity, while B is all the numbers from negative 2 to 2. So in this one you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to a billion to infinity. In this one you have negative 2, negative 1, 0, 1, 2, 1.5, 1.7, negative 1.7, and so forth. What numbers do they share on there? Well, the smallest I can go that's in both of them would be 0. While the largest I can go that's in both of them, this one goes up to infinity, but this one only goes up to 2. So it's just from 0 to 2. And that's going to be my domain all the way down. Except for this last one. How's it going to change? Let's think about it. We have to make sure that the bottom's not equal to 0 right here. So it's still okay to plug in 0. But one change on it is going to be if I include this 2 by putting a bracket on there, and I plug a 2 down there, it's going to give me a divide by 0 error. So I just don't want to include the 2 that time. That would have been a good erase all opportunity to quote a student from last year. I'm going to start remembering that. Given two functions f and g, the composite function, okay, now this is composite function. This is going to be where we have the, I should have put a toaster on here. It's going to be where we start over here with an x, okay, and it's going to map over to this middle guy right here. We're going to call it g of x. So I think of it as we take the bread and we're making French toast. So I'm going to dip it in the egg. Okay. Now if I dip the bread in the egg in the process of making French toast, it has to come out as soggy bread at this point. Now what's going to happen is it's going to go through another machine. It's going to go into the skillet, if you will, and it's going to come out as f of g of x. So I'm mapping it twice. I'm doing two functions on it, okay? And so the way that we write it is we can write f of g of x just like you saw it down here. Or the way the book's going to write it is f of g of x. So all in all, what we're trying to do is find a way to go straight from the bread to the French toast and skip this middle guy. Once we find a formula for it, we call it f of g, or f composed of g. Again, I think this is going to be kind of a review of what we did last year. If I have f of x and g of x are listed as those functions, I'm wanting to find f of g and g of f. I'm going to do one of them, have you do the other. I'm going to do f of g of x. And so the first thing I do is I rewrite it. I don't like that where it looks like fog. I would rather see it like this. And there's many ways, there's a lot of shortcuts of working this where you can work it in maybe one step, two at most. But I'm going to go ahead and work it the long way. I'm going to do my direct substitution step first. So I still got my f right here. But what I'm going to do is I'm going to take out this g of x, and I'm going to write what g of x is equal to, x minus 3. Now it works like the difference quotient did a couple of weeks ago. Instead of f of x, I have f of x minus 3. So I'm going to do another substitution. I'm going to take this x minus 3, and I'm going to plug it into my f function for this x. So I get x minus 3 squared. I just took out the x, put x minus 3 in its place. I would be hard-pressed to count that wrong. If you want to expand it, that's pretty cool. I don't know if that looks a little bit better or not. I'll accept either of those bottom answers. You try it in reverse. You think you're going to get the same answer, but you're not. All right? It's not reflexive that way. So go ahead and hit pause on the video, and then you give g of f a shot. All right, I think I'm playing again. I accidentally marked on my thing down there. Let's see, it should be playing. Yeah. You got the easy one, all right? You didn't have any expansion to do, but yeah, it's just plugging it in reverse. Hopefully you got x squared minus 3. Okay. Now, there wasn't any domain restrictions on the other one. If you look at x minus 3 and x squared, they both have a domain that goes from negative infinity to infinity, so it's not too hard to figure out what's going on and what goes where. But let's look at one that has a domain restriction on it. Okay, I want to talk about it, and I'll show you a shortcut that sometimes works. So, which one I want to do? I'm going to do f of g of x. I'll let you do the g of f of x in just a minute. So f of g of x, I have f of, my direct substitution says plug in g of x, square root of 2 minus x. Okay. Now, if I do f of that, I'm going to take this, I'm going to plug it in for this x. Well, it's already got a square root, so I get the square root of 2 minus x. I haven't talked about this too much, but if you take the square root of something, that is the same as taking the fourth root of 2 minus x. And so the domain on this isn't going to be very hard. It's kind of weird, but I'm able to do the domain just by taking 2 minus x and making sure it's greater than or equal to 0, since it's underneath an even root. If it's underneath an even root, and I solve it for x, I get x is less than or equal to 2. Less than or equal to 2 is going to be all the numbers from negative infinity to 2. One thing you want to do on this is you want to go back up and make sure that this same idea works for each step that's underneath the square root going up. Okay. Okay. So let's try g of f of x. You give it a shot. You try the domain on it, and then we'll see if we get the same answer. So go ahead and hit pause. Did you actually work it, or did you just let it keep on playing? I got to here, and so if you wrote negative infinity to 4, that's not a bad answer. But what I want to point out on this little shortcut is that I had to work it in reverse also. I want to look at the domain that's coming with this step right here, because this step right here, I won't make it very far unless x is greater than or equal to 0 as well. So if I take these two and combine it, I take the fact that x has to be less than 4, and I take the fact that x has to be greater than or equal to 0, I'm going to get my domain to be 0 to 4. So you kind of have to backtrack. It's everything that's in the domain of this inside right here that's also in the domain of your final domain. Okay. If you have questions on that, make sure you ask. That domain on composition of functions is very tricky. Ooh, what if I throw 3 parts up there? I'm not going to worry about domain on this one. But the first step I am going to do is I am going to rewrite this as f of g of h of x. So yeah, this one's going to be a little bit harder because it's got 3 parts in it. But we did do some of these last year. So again, I'm just going to start on the inside and work my way out. So I have f of g of h of x is x plus 3. Next, I'm just going to take this x plus 3 and plug it in for g. So I'm just going to take out this x, and I'm going to put x plus 3 to the 10th power in its place. And then finally, I'm going to take all of this, I'm going to plug it into my f. Well, what's my f? Well, I got a couple x's on there. They would be x plus 3 to the 10th over x plus 3 to the 10th plus 1. That'll work for the final answer. I know earlier I expanded my binomial, but that was just raised to the power of 2. It wasn't too hard. This one's raised to the power of 10. If you want to expand that out, it'd be fun for somebody, but this will be all I check on that because I probably won't even have it expanded all the way out. Let's work one in reverse. I like working stuff forwards and backwards. On this one, they told me what the composite function was. So on this one, this guy right here is going to be f of g of h of x. I want to break it down into it telling me what, or I tell it what f of x is, and what g of x is, and what h of x is. Now, first of all, I want to point out there's no cheating, all right? There's no going through and saying, this is x, this is x, this is cosine squared of x plus 9, all right? Can't do that. That's no good. That will work every time. So you're not allowed to use the identity function on any of these. But I can still use the same idea of starting on the inside and working my way out. And I see that this h right here is on my very inside. So I want to find what's on the very inside of this function right here. I think it's x plus 9. What's next on it? It's going to be my g. Be careful on this, because I could actually rewrite this. Remember, the mathematicians got lazy. Oh. We actually already messed up, didn't we? Because that cosine squared means that I'm taking all of this and squaring it. Oh, so we didn't mess up. So what's on the inside would be this x plus 9, but what's happening next is I'm actually taking cosine of the x plus 9. Just imagine plugging that x plus 9 in for that x. I would have the inside part of this function. Lastly, the very last thing that we're doing is that we're squaring our result, the square that's on the outside. So these three would be my basic functions broken down from this big composite function. Here's homework for the week. Make sure that you talk to me about this. I got a special surprise for you when you guys get to this that I think you guys will like. So good luck. If you have questions on it, jot them down, put them on the board, ready to go for next time that we're in class.